So welcome to all. Myself Dr. Santhosh Singh, working as an Associate Professor in Department of Physics, Institute of Aeronautical Engineering. Today I am going to discuss about Fermi level. So let's start with it. So you know that the electrons are distributed among the available energy level in any solid or any material with the help of this distribution function. Actually, this is the probability distribution function. The other name is Fermi-Dirac distribution function. So, by this law or by this rule, your electron will be distributed in energy level. This thing I already told. So, for obey this law, the electron, obviously the electrons are indistinguishable particle, and also they follow the Pauli exclusion principle. So, for obey this law, this such type of property, the particle must have purges. Means they must have indistinguishable and they must have follow the Pauli exclusion laws. Pauli exclusions principle or law. So you know that your electron are indistinguishable particle and also they obey the Pauli exclusion principles. So you can say that this distribution function can be worked for electron distribution for available energy levels. So this distribution function f of E is equal to 1 upon 1 plus e to the power E minus EF upon KT. Okay, where K is Boltzmann constant and this E is on what energy level you want to distribute your electron and what will be the probability for occurrence of that electron in that energy level. That E is such energy level. This EF is your Fermi energy. So today I am discussing about this Fermi level. Okay. So the energy correspond to Fermi level means your Fermi level can shift from one position, one energy level to another energy level. So corresponding energy is known as Fermi energy and corresponding energy will also shift corresponding to Fermi level shifting. Means if this is your Fermi level EF, so the corresponding energy value E is known as Fermi energy. So the Fermi level is important and the corresponding energy is known as Fermi energy. Okay, so I will discuss today some fact about Fermi level. Okay, so you know that the probability of occupancy or probability distribution function of electron in energy level is given by f of E, and same time you can also calculate 1 minus f of E. What will be the probability for unoccupied energy level? Okay, means what is the probability of energy level E which remains unoccupied? If f of E giving the probability for occupation means an energy level E, the probability for energy level E can be occupied with available particles or in the case of solid available electron. So this is the probability for occupancy. So the corresponding probability for unoccupied level will be given by 1 minus f of E. Okay. So f of E, the form or expression of f of E, several times I told, again I am writing f of E means distribution function value expression is 1 upon e to the power E minus EF upon KT plus 1. Okay. Now where this EF is your Fermi energy. Now let's discuss about the case when E is equal to EF. Okay, what happened? Now put E is equal to EF in this expression. What you will get? You will get F of E is equal to E to the power EF minus EF upon KT plus 1. So this whole expression, this exponential term becomes 0. 1 plus 0 plus 1 is equal to E to the power 0, E to the power 0 plus 1. So E to the power 0 is 1. So this whole term becomes 1 by 2. Okay. Now once you are putting the E is equal to EF, E is equal to EF, what you are getting? The probability for occupied these levels means E is equal to EF is how much? Is equal to 1 by 2. So you can define your Fermi level with the help of this probability also. So what is your Fermi level? So Fermi level is that level where the probability for occupancy is 1 by 2. Okay. Means there is 50-50% chance so that that particular level will be occupied by any particle. In the case of solid, that level will be occupied by electron. So what is your Fermi level? Fermi level is that energy level where the chance for occupancy is 1 by 2. Okay. Chance means probability. So, but this case will be different at absolute zero temperature. What happen at absolute zero temperature? You know that from your solid state physics course that at absolute zero temperature, all the balance band level will be completely filled and all the conduction band's energy level will be completely empty, unoccupied. So you can, if you are drawing some energy band diagram, and let's say this is your valence band region and this is band age energy EV, and let's say this is your conduction band, and let's say this is your conduction band age energy EC. So whatever the energy level available in the valence band will be completely occupied by the electrons. Means all the energy levels are filled. Okay. And whatever the energy levels available in the conduction band that are completely empty. So in the form of distribution function where f of E is equal to 1 upon E to the power E minus EF upon KT plus 1. Now I am talking about T is equal to 0 Kelvin. Okay. So now put T is equal to 0 Kelvin, but remember the case, your EF will be that energy level where the chance is 50-50. The chance of occupancy is 50-50. But here, your all the energy levels are completely filled. Means here the chance is completely 1. And if EF is that level where the chance is 50-50, so definitely it will be lie above this valence band region. It will definitely lie above this valence band region. Okay. It will never be the part of this conduction band. Why? Because here the chance is completely 0. But in the case of, if I am talking in the term of Fermi level, definitely there will be the chance of 50-50. Means that level may be filled by or may be unoccupied. Okay. So that EF will be in between somewhere, in between the conduction band and balance band. But what happened at 0 Kelvin? So definitely all the energy levels which are coming under the part of balance band VV have the less energy than EF. So for the case when E is less than EF, and if E is less than EF and your temperature is equal to 0 Kelvin, what will be the form of this expression? F of E. So F of E is equal to 1 upon, now E will be less than EF. So this whole term, something negative value will become e to the power some negative value, some, let's suppose n. What will be the difference? E minus EF. So E is less than now EF. So E minus EF will, some negative value will become, let's suppose minus x upon K multiplied by 0. Okay. So plus 1. So what will be this term will come? E to the power minus something negative upon 0. It will come like e to the power minus infinity plus 1. So e to the power minus infinity is 0. So you can say 1 by 1 is equal to 1. So from this distribution function, it is also clear that whatever the energy level which will be the part of valence band will be completely filled. Why? Because the chance for occupancy is 1 there. Probability for filling the energy level for those energy levels which have the value less than EF is 1. So all those energy levels is a part of valence band. Okay. So you can plot this thing F of E F of E you can plot this F of E. So its value will be 1 for certain energy value where E is less than EF. All the energy levels will be completely filled. Okay. Now at the same time at T is equal to 0 and E is equal to EF, what happened? What I am telling, you discuss this case, E is less than EF at T is equal to 0. What happened when E is equal to EF and T is equal to 0 Kelvin? So your probability distribution function F of E is equal to 1 upon e to the power E minus EF upon KT plus 1. So put the value is equal to EF, 1 upon e to the power EF minus EF on KT. So K multiplied by 0 plus 1. So something e to the, what you will get? E to the power 0 by 0 plus 1. 0 by 0 you can say 0. So you can Actually 0 by 0 is a kind of undefined thing, but you can say 0. So e to the power 0 is 1. So at the energy value E is equal to EF, and at T is equal to 0 Kelvin also, Fe is equal to 1. At T is equal to 0 case, normally when E is equal to EF, F of E, I calculated earlier, F of E is 1 by half. There is 50-50% chances. But at the case when T is equal to 0 and E is equal to EF, F of E is equal to 1. So you can modify your definition for Fermi level for absolute 0 case. So your Fermi level in that case is that level, means at absolute 0 temperature case, your Fermi energy level is that energy level which have also occupancy value, chance of occupancy value is 1, and it will be the highest field level, and you can say it is the part of valence band. Actually Fermi level generally will be not a part of conduction band as well as not a part of valence band, but in the at absolute 0 case you can say that it is the highest field level, and it is the part of, you can say it is the part of valence band. So there are two graphs, F of E for certain energy E is less than EF. So for this region, F of E is 1 at T is equal to 0 Kelvin. Okay. What will happen for E is equal to EF at 0 Kelvin? E is equal to EF will also giving the same result. Means this energy, EF energy value, EF energy value level is also giving the same value of F of E. Okay, means F of EF at T is equal to 0 Kelvin is also 1. So you can modify this graph in the form of EF, and F of E is equal to 1 at T is equal to 0 Kelvin. So up to EF energy level, all the energy levels will be completely filled, means the chance of occupancy of electron will be 1. Okay. So normally your definition of Fermi level is what? Those energy level will be considered as a Fermi level where the chance of occupancy is 1 by 2 or 0.5. But at absolute 0 temperature, means at 0 Kelvin, chance for occupancy for even Fermi level will be also 1, and your Fermi level will be considered as a part of valence band. Okay. And apart from the Fermi level, all the available energy level will be remains unfilled, means the probability will be 0 for chance of occupancy will be 0. So that is the some discussion, some fact about Fermi level. Now the same thing is written here. What happens once we are increasing the temperature, effect of temperature on Fermi level? So you can see by this plot, and also you can visualize the effect of temperature by this expression e to the power E minus EF by kT plus 1. So this rectangle is the graph which is occurring on at absolute 0 temperature T is equal to 0 Kelvin. Now what will happen if you are increasing the temperature T? Okay, so T is greater than now 0 Kelvin. So there is the two case. One is for E is less than EF, and another case, second case will be E will be greater than EF. So now T is not absolute 0 Kelvin. T is something higher than 0 Kelvin. So you have to again switch your definition of Fermi level. Now your definition of Fermi level is that that level will be considered as a Fermi level where the chance of occupancy will be 1 by 2. Okay. So if this is that energy level means EF, so the corresponding chance F of E will be how much? It should be 1 by 2 at T is greater than 0 Kelvin. Now what about the others region? Means others energy level means what about for energy level which have a lower value than EF, and what about those energy level which have greater value than EF? So which have greater value than EF will come in this region, and which have lower value than EF, that energy level will come in this region. So what will be the probability distribution, probability for these levels, so that these levels will be occupied, are also about these levels, so that these levels will be occupied. So see that once you are, this rectangle is representing the probability distribution function at T is equal to 0 Kelvin. Once you are increasing the temperature, like this graph is for T1, this one is for T2, this one is for T1, and obviously this is for T2, this is for T1. So this T2 temperature is greater than T1. So see, this curve is for T2, this curve, and this curve is for T1. T2 is greater than T1. So at higher temperature means at temperature greater than the 0 Kelvin, we are considering two temperature T1 and T2, and in between these T1 and T2, T2 is greater. So at T1 temperature, which is obviously greater than 0 Kelvin, see, whatever the energy levels present below the EF, some energy level, have a probability less than 1. Means there is the chance that these levels will be remains unoccupied. Obviously, the chance for occupancy is also there and even greater than 1 by 2, but there is some chance. If let's suppose this is 1, this is 1 by 2, so let's suppose this is around 0.75. So there are 75% chance that these level will be occupied, but still there are 25% chance so that these level will be unoccupied. And I am taking for this T1 temperature. Now, if I am considering the curve for T2 temperature, and I am also considering the case when E is less than EF, Means I am talking about those energy level which have a lower value than Fermi energy. So chance for these level so that they will occupy it will again reduce in comparison to T1 curve. In comparison to T1 curve. Okay, where T1 is great, T1 is less than T2. Means what from these discussion, what you can conclude? Chance for occupancy in on the energy level which are having the lower value than EF will be decreased at higher temperature. Okay. Now what happened for the case E is equal to EF? So what happened for those energy level which have the value greater than the Fermi energy? So these levels will come in this region. So at T1 temperature and that T1 is less than T2. So this is your T1 curve. Now for these energy level, the chance will be for T1 is this much, some value around 0.25 or 0.30. But same energy levels, chance for occupancy for same energy level at temperature T2 will see enhanced comparison to T1 curve. Okay, means what you can conclude. So the chance for occupancy for those energy level which are having the energy value greater than EF will increase at higher temperature greater than the 0 Kelvin. So if you are increasing temperature more and more, the chance for occupancy for those energy level which are having the energy value greater than the Fermi energy will be increased. Chance for occupancy for those energy level will be increased which have the value greater than the Fermi energy. Okay. Now, so at temperature higher than the 0 Kelvin, some probability exists for the states above EF to be filled. For example, at T is equal to T1, there is some probability F of E that states above EF are filled. And there is a corresponding probability 1 minus F of E that states below EF are empty. Okay. Means there are some chances so that here the states are empty. So same chances that here the states will be filled. Means this distribution function if this is the rectangle kind and if any smearing happen, so these area and this area will be same. Okay, what is this area? This area is representing that is there are some chance that these energy levels will be occupied, and this region is representing that there are some chance that the energy level which are present here will be maybe remains unoccupied. So this region will be filled by some electron. There are some chance. So that's why F of E, and this region is 1 minus F of E, you can say. Chance for unoccupied level. So what I am trying to say, these regions will form a symmetrical curve around this line. Means this area of this region will be same as area of this region. Okay. So the same thing I already discussed here. Okay. So the Fermi function is a symmetrical about EF. Fermi level, Fermi energy level. Fermi function are F of E, Fermi Dirac distribution function or probability distribution function. F of E, this function 1 upon e to the power E minus EF upon KT plus 1 is symmetrical about EF, this energy level. This is what EF, where the chance is always 1 by 2. This is at T is equal to 0 Kelvin. So this curve is symmetrical about the Fermi energy level EF. Okay. So the Fermi function is symmetrical about EF for all temperature. That is the probability of F of EF plus delta E, that state delta E above the EF is field is same as the probability of 1 minus F EF minus delta E. That is the state delta E below the EF is empty. Okay, means these area and these area, means chance for unoccupied level and chance for occupied level over both sides of Fermi energy level will be same. Okay. So the symmetry of the distribution of empty and filled state about EF make the Fermi level a natural reference point in calculation of electron and hole concentration in semiconductor. So based on this area, this probability, you can calculate the carrier concentration. Okay, means whatever the electrons will leave the valence band energy level and reach to conduction band region. So that vacant level, the holes will be generated, and same amount of electrons will be now accommodated in conduction band region. So that's why the symmetric about this Fermi level, and this Fermi level will provide the reference point for calculating the carrier or electron and hole concentration in semiconductors. Now I will talk about intrinsic. Intrinsic semiconductor, N-type semiconductor, and third one is P-type semiconductor. So I already discussed what is intrinsic, what is N-type, what is P-type. You can see this thing in my previous video. I will talk these semiconductor in term of Fermi level. What will be the position of Fermi level in intrinsic semiconductor, in N-type semiconductor, and in P-type semiconductor? So for intrinsic semiconducting material, we know that the concentration of holes in the valence band is equal to the concentration of electron in conduction band. Means N of E is equal to N of P. Okay. Therefore, the Fermi level EF must lie at the middle of the band gap in intrinsic material. Okay. Because what I told, this F of E will be symmetric about EF. Means this area will give the probability for occurrence of holes. Why? Because these levels will be remains unoccupied, and are if at T is equal to 0 Kelvin, these levels are populated, and at some higher temperature, some electrons are migrated from these levels and shifted here in conduction band region. So the holes are created. So this area, this probability will give the chance for occurrence of holes, or you can say in other words, concentration of holes. And this area, obviously, now these levels are populated, so you can calculate by this area, with the help of this area, you can calculate the concentration of available electrons, free electrons in conduction band. So in intrinsic semiconductor, carrier electron concentration as well as hole concentration are same, equal. So that's why I wrote N of E, concentration of electron is equal to concentration of hole. So see here, I also show the variation of Fermi level, F of E variation, about both sides of Fermi level. So in intrinsic case, if N of E is equal to N of P, this region will be same area than this comparison to this region. Mean these two area, this area and this area. What is this area? This area is representing this whole area is representing the chance for occurrence of electron above the Fermi level, and this whole region is providing the chance for unoccupied region below the Fermi level. Means there here is the chance so that the holes will be generated. Okay, from here to here, from whole this region. Let's say again, from this region to this region, there is the chance so that the hole can be generated, because there is the chance that the levels may remain unoccupied. And here in this region above the Fermi level, there is the chance that your levels will be filled. Okay, so from above the Fermi level up to the bottom of conduction band, this whole region, you can calculate the carrier concentration of electron with the help of this whole region. Okay, and that's why they show this region, particularly which are coming under the conduction band region, by this big figure. Means there are still some chance here, there are some probability so that the levels will be occupied. Okay, so the corresponding in valence band region, there will be definitely some chance that some labels will be remain unoccupied. So overall, this f of e, probability distribution function of electron in over energy region E, is making a kind of symmetrical curve about EF energy level. Okay, why? Because n of E is equal to n of P. Concentration of electron in intrinsic semiconductor is equal to concentration of hole. Okay, so that's why this chance for occurrence of electron in conduction band will be same as chance for occurrence of hole, means unoccupied level in valence band is same. Okay, so that all the thing is written here. So for intrinsic material, we know that the concentration of hole in the valence band is equal to the concentration of electron in conduction band. Therefore, the Fermi level EF must lie at the middle. Why must lie at the middle? Because then only it will become a pure symmetric in nature about EF. So that in both region, means in conduction band region and in valence band region, there are equal chance for getting the holes and electron. Okay, so that's why it will be perfectly lie at the middle. Now since f of E is symmetrical about f of E, since f of E is symmetrical about Fermi energy EF, the electron probability, means tail of this f of E extending into the conduction band, is symmetrical with the whole probability 1 minus f of E in the valence band here somewhere. Okay, the distribution function has a value within the band gap between EC and EV. This distribution function also have some value. This is the f of E curve, and this curve have some value between EC and EV, obviously some value, but it doesn't mean there are some energy level except EF. One level is definitely present, that is Fermi level or Fermi energy. But apart from this Fermi level, there is a no level. Even f of E means chance for occurrence of atoms there, but there is a no energy level. So based on f of E, you can't say there must be some energy level. F of E is only telling if that energy level is available here, what will be the chance so that any electrons can occupy these energy level. F of E cannot confirm that there must be some energy level. Even their value is even 1 or near to 1, you can't say there must be some energy level. This is if there is the energy level, what will be the chance for that energy level so that it will be occupied by electron. That thing only f of E can tell. Okay. Now the next case is for n-type semiconductor. So in n-type semiconductor, you know that the n of E is greater than n of P. Okay, or carrier concentration or electron concentration in a conduction band is greater than hole concentration in valence band. Okay, means there are some unsymmetrical distribution definitely happen. Okay, so for getting some unsymmetrical distribution, wait 1 minute, I am plotting the curve. This is the case of intrinsic. Now I am discussing about the case for n-type semiconductor. So n-type semiconductor, you know that you have to dose some impurity for getting the N-type semiconductor. Means you have to dope some fifth group element in intrinsic type of semiconductor like germanium and silicon for getting the N-type semiconductor. So the effect of doping take place. Okay, and due to that effect only the concentration of electron in conduction band will increase. Otherwise, in an intrinsic case, I could not draw the correct figure here. Let's suppose this is the intrinsic case where I want to make these two area equal in size so that the chance or probability should be equal for intrinsic case. Okay, but now I am discussing about the case for N-type semiconductor. So in the N-type semiconductor, if this is the chance for availability of electrons, this region, this area is indicating the chance for availability of electron. So for N type of semiconductor, this region should be greater than this region because the carrier concentration of electron is greater than the carrier concentration of hole in N type semiconductor. So how it is possible? It will be only possible when your Fermi level shifted towards the conduction band. Okay, here the figure is given already because some exact symmetric thing is required and I could not draw with the help of such type of pen. So see here, your Fermi level is shifted near to the conduction band, and if you are remember this intrinsic case, your EF is exactly situated at the same distance from valence band and even same distance from the conduction band. Means exactly at the middle of band gap region. Okay, but here your Fermi level, this is your band gap region, EG. This Fermi level is now got shifted near to conduction band or conduction band age energy. So what happened? The chance for occurrence of electron, this region is now increased comparison to chance for occurrence of hole here. Okay, here it is completely flat. Okay, if the level will be unoccupied here in the balance band, then there is the chance that hole can create here. Now see here, you are getting here completely flat f of e, and it is nearly 1, means all the levels are completely filled. But here you are able to see there are some chance that these levels are filled. Here we need to calculate the chance for unoccupied level. Unoccupied level. And these levels will give the concentration about carrier concentration value for holes. Okay, but here what you are saying, all the levels are filled, means there is no chance so that the holes can create here in the balance band. But here there is some more chance comparison to this region, so that the levels are filled by electrons. Okay, means if these levels are filled by electrons, means number of electrons, available number of electron for conduction is greater than available number of holes, or available number of electron in conduction band will be greater than available number of holes in valence band. Okay, due to this shift, and this shift happens due to the doping. This is not the material property. This label, this is EF, will come from the doping or dopant level, you can say. Why? Because in intrinsic case, the Fermi level will maintain this behavior. This is the inherent property for particular any considered material. But if you are doped that material with some external doping agency or doping agent, you can see that your Fermi level got shifted, and obviously you have to, for getting the N type of semiconductor, you have to dope such type of material so that you can get N type behavior, means number of electron will be more high than number of hole. So how you can get the N type of semiconductor? If you are dope the intrinsic semiconductor with fifth group element, means if you are doped silicon or germanium with fifth group element, maybe you can able to get the N type of semiconductor, and such N type of semiconductor will have a large number of electron comparison to holes. And why it's happened? Because the Fermi level got shifted near to the conduction band, and there is some chance so that the energy level available above the Fermi energy, whatever the energy level, some energy level available above the Fermi energy level can be populated or may be occupied. Okay, and due to that occupation, the number of electron will be increased. Okay, so the symmetric shape of this F of E will not remain same in the case of N type or P type semiconductor. It will change. Okay, so since F of E retains its shape for particular temperature, the larger concentration of electron at EC in N-type material implies a correspondingly smaller hole concentration at less than E of V, or at E of V. E of V means balance band energy, this energy. Where the balance, below this energy level, your balance band region are present. Or you can say up to this region, from something bottom side to up to this region, your balance band region are present. So near to or at EV, 1 minus F of E is obviously very less. So that same thing is written here. Since F of E retain its shape for particular temperature, the larger concentration for electron at EC in N-type material implies a correspondingly smaller hole concentration at EV. Okay, and we noticed that the value of F of E for each energy level in the conduction band, and therefore the total electron concentration N naught increase as EF move closer to EC, conduction band age energy. This is your EC. Okay, and thus the energy difference EC minus EF gives, try to give the, with the help of this EC minus EF, you can calculate the carrier concentration. And carrier concentration means here obviously your majority charge carriers is electron, so you can calculate the electron concentration. Now the same thing happen in p-type semiconductor. Once you doped with third group element with intrinsic semiconductor, you will get your p-type semiconductors. And what happened in this case? In this case, your Fermi level got shifted towards the valence band or near to EV, valence band age energy. Okay. And due to this, what happened? Near to EV, there are some chance so that the levels will be remains unoccupied, and so that the holes will created. Okay, holes will created, but near to EC, it is completely, f of E is completely C 0 or near to 0. Okay, so this region or this unoccupied energy levels or chance for unoccupied energy level will provide the carrier concentration of holes, and obviously it will be greater than N of E in p-type semiconductor. Okay, so here 1 minus f of E tail below the EV is larger than f of E tail above the EC. Okay, so the value of EF minus EV indicates how strongly p-type the material is. Means if this region will be greater, your whole carrier concentration, availability of hole per unit volume will be more. Okay, so such that 1 minus Fe, this region, here something up to this region, 1 minus Fe tail below the EV is larger than the f of E tail above the EC, something here. So the value of EF minus EV indicate how strongly p-type the material is. Okay, it is usually inconvenient to draw f of E versus E on every energy band diagram to indicate the electron and holes distribution. Therefore, it is common practice merely to indicate the position of EF in band diagram. Means with the help of EF, position of Fermi level, you can say this any material is either it is p-type or n-type. Based on position of Fermi level, you can conclude about the material it is p-type or n-type. And even based on position of Fermi level, you are able to calculate the carrier concentration. We will see this thing how we can calculate with the help of EF, position of Fermi level or energy of Fermi energy value, how we can calculate the carrier concentration. So thank you. That's all for today's video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.